Welcome back. Today we're going to prove the most important property of similar triangles, and that is their proportionality. So let's start with what does this mean? First of all, triangles are called similar when they have equal angles. So in this figure, angle A matches angle D, angle F matches angle C, angle E matches angle B. So similarity is a statement about angles. Proportionality, on the other hand, is a statement about lengths. It's a complicated statement about the ratios of lengths. So let me be specific about what exactly proportionality means. So on the one hand, it means that the ratios taken from one triangle to the next triangle agree however we take them. So if we say ABC is proportional, so triangle ABC is proportional to triangle DEF, one thing that this means is that AB, this length compared to the corresponding length DE, is equal to any other corresponding lengths. So AC compared to DF, or BC in ratio to EF. So notice these are all corresponding ratios. So these are ratios across from one triangle to the next. AB divided by DE. And that ratio, which is 18, so in the example shown here, what this would mean is that 18 over 42 is equal to AC over DF would be 14 and a half over 34, and that should be approximately equal to 7 over 16.5. And each of these ratios is a little under 1/2. And if you actually work it out on a calculator, you'll see that these are not exactly equal because these are slightly imprecise measurements, but they are in principle equal if I draw the diagrams perfectly and measure them perfectly too, which is a tall order. Here we have the equality of ratios across from one triangle to the next. But there's another interpretation of proportionality, and that is that we take the ratios not across from one triangle to the next triangle, but within one triangle. So in other words, we would take the ratio, for example, AB over AC. So we would take this ratio and compare it to this ratio. We would take this length and compare it to this length and produce a ratio of lengths within the triangle. And then that should agree with an analogous ratio of lengths within the other triangle, in this case, DE over DF. So DE over DF. The triangles match up. A corresponds to D, B corresponds to E, C corresponds to F. And so you should be able to just think alphabetically here, replace the A's with D's, replace the B's with E's, replace the C's with F's, and get the corresponding ratio of lengths within the other triangle. So this ratio within the triangle will equal this other ratio. So in the specific numbers that we have here, 18 over 14.5 should approximately equal DE, that is 42, over DF, which is 34. And both of these ratios are slightly more than 1, perhaps maybe 1 1/4. So these are two different perspectives on what proportionality means. Now, it might seem strange for me to say, oh, well, maybe it means this and maybe it means that, and you've got alternatives here. It should mean one thing definitively, right? But there's really not all that much difference between these statements. So I want you to compare how easy it is to get back and forth between these statements. So let me highlight here this equality, which is an equality of ratios across from one triangle to the next, and this equality, which is an equality of ratios within one triangle compared to this corresponding ratios for the other triangle. So what is the relationship between these things as equations? Super simple. All you have to do is divide both sides by AC to move it to the other side, multiply both sides by DE to move this to the other side, and you can translate this algebraically into this. So algebraically, so geometrically, it feels like there's a difference between these statements because this is across from one triangle to the next. This is within one triangle. Algebraically, there's no significant difference between this equation and this equation. And so we don't really have to care which one of these things we mean because they're obviously equivalent. So this is what proportionality means. And the statement that we're going to prove today is that similar triangles are proportional. That is, if the angles are equal, then we will have these equalities of ratios. Now, how many equalities of ratios do we have? In principle, we have lots, right? We have this equals that, and we have this equals that, and we have this equals that, right? So how many things do we actually have to prove here? In fact, we only have to prove one. We will prove this one, and we'll just get an equality that sort of focuses on the points A and D as the important points leading to the segments that we want to calculate the lengths of. And then once we get one of these things, then if it's true generically in one way, then it's also true generically in all of the other ways. So one is enough to represent generically the equality of ratios that we need here. So, so let's get started here. In order to do this, we're actually going to need, it doesn't look like it, but we're actually going to need the area formula for a triangle. So I want to recall this, not because you don't know it, but I want to call your attention to it. So recall area of a triangle is 1/2 base times height. We're going to use this in lots of ways in this proof, and so I want to call your attention to it. This is not something whose proof is going to appear in this video, but it will appear in a different video. So, but of course, I know that you know that already. So let's get to the proof of the proportionality of similar triangles. How do we do this? Well, the first inconvenience that we have to deal with is that these triangles are potentially separated. A and B and C and D and E and F are 6 different points in the plane, and they have no relationship to one another. And so it's hard to compare. It's easier to deal with the relationship between two triangles if they are overlapping or partially overlapping. And so, well, we can't, well, I mean, with transformational thinking, we can think about moving this, but I want to think about this in pure congruence level thinking. And so instead of thinking about this as a motion of the triangle ABC, I want to just think of it as a reconstruction of a copy of the triangle ABC in such a way that the copy will overlap with DEF in a convenient manner. And so what we're going to do is we're going to construct a new version of a triangle here, a third triangle, A prime, B prime, C prime. It'll turn out to be congruent to ABC. So it's basically just another version of ABC, but it will be positioned conveniently. So I need to construct some points here. So the first point I'm going to construct is I'm going to construct A prime. I'm going to let it be equal to D. So let A prime equals D. So in other words, they're going to automatically overlap in that they share this point. Then I'm going to choose B prime somewhere along the ray DE. And I'm going to do it so that I get the right length A prime, B prime. So we're going to let B prime be on the ray, let's call it DE, so that A prime, B prime equals AB. In other words, you know, if you think about this in terms of measurement, I'm going to measure this length, 18 centimeters, and then I'm going to go here, and I'm going to identify 18 centimeters, and I'm going to choose another point that's 18 centimeters from A prime, and I'm going to call that B prime. And now, if you're thinking about what's going to happen next, then you're probably thinking, I'm going to measure this length, 14.5, and choose C prime to be 14.5 from there. And you would be right, that would work, but it's not the most convenient way for us to phrase what's really going on. The most convenient way to express what's really going on here is to construct C prime in a slightly different way. And that is by just guaranteeing, so the thing is, if I measure this distance, 14, and I choose C prime here, I will wonder for a long time whether this line worked out to be parallel to this line. I suppose it probably will, but it might be a little inconvenient to prove that it did. And so what I really need is the parallelism. And so instead of choosing C prime to be the same length from A prime, I'm actually going to construct a parallel line here, and I'm just eyeballing it, but I'm going to construct a line through B prime parallel to ED. And I think I did that a little bit badly. So let's correct it a bit. So I'm going to construct a line through B prime parallel to DE. And then wherever that happens to meet DF, that will be my point C prime. So let's record that. So let L through B prime be parallel to EF. And let C prime be the point of intersection between the new line L and the old segment DF. So now we have C prime, and now by construction, we're guaranteed that these two lines are parallel. Why do I care so much to make so, why do I want to be so very careful to make sure that those two lines are parallel? It's because I want the angles to work out well. So this line DE now becomes a transversal that cuts two parallel lines. The lines are this line L and the line EF that already existed. This thing is this DE line is a transversal across two parallel lines. And that means that this angle here and this angle here must agree with each other because they're corresponding angles of a transversal cutting two parallel lines. And so let's note that. I'm going to call this angle B prime for short. Technically, that's ambiguous because there are two angles formed at B prime, but you know what I mean. It's A prime, B prime, C prime. So this is angle A prime, B prime, C prime. That's equal to angle E. I can safely call this angle E because there's only one angle represented there at E. And furthermore, for the same reason, angle C prime, which really means angle B prime, C prime, A prime, is congruent to angle F. This is for the same reason. We've got these two parallel lines here, and then they're cut by this transversal DF. And so these two angles here are equal to each other. And then I could state that angle D and angle A prime are equal, but it's so obvious I don't even need to state it. Now, that means that the triangle A prime, B prime, C prime shares angles with triangle DEF. And so what does that mean? Triangle A prime, B prime, C prime is similar to triangle DEF. I point this out in other places, but I want to remind you that this statement of similarity is an ordered statement. That means angle A prime is not equal to just one of these, but specifically the D, and B prime is equal to E, and C prime is equal to F here. So we get a similarity there, but of course we already have the similarity with the original triangle ABC. So ABC. So triangle ABC and triangle A prime, B prime, C prime are similar. Of course they are. They were built that way, right? A prime, B prime, C prime was built to be a copy of ABC. Is it indeed congruent? Well, remember that we constructed A prime, B prime at least to agree with AB, right? This one is guaranteed to be 18. I have no idea how long this is or this is. I didn't calculate that. I didn't rig that, but I rigged this to be in agreement with that. And if I've got all the angles equal in one length, then I can use the angle side angle congruence. So triangle A prime, B prime, C prime is congruent to, that's a pretty bad congruent symbol, is congruent to triangle ABC by the angle side angle congruence criterion. So this angle at A prime, this side at A prime, B prime, and this third feature, the angle at B prime. So in other words, so the whole process is about copying this triangle to here so that it works out more conveniently, so that they overlap in a nice way. Now that they overlap, we still have a lot of work to do. We need to show that the ratios are equal. So what we're going to try to do is we're going to compare the ratio A prime B prime over DE to the ratio A prime C prime over DF. Now, we're going to need some auxiliary triangles here. So let me draw them in. I'm going to need to draw B prime F, and I'm also going to need EC prime. So I'm going to need these crossbars in the figure. I've identified two crossbars in purple, and I've shaded two triangles here. One of them hash marks in green and one of them in blue. To try to help you identify two new triangles in this picture. They are B prime FE and C prime FE. So, so what do we know about those triangles? They're not at all congruent, as you can tell by looking, but they do have the same area. So I'm going to record that this way. I'm going to say, note, I'm going to use the parenthesis notation for the area. So B prime EF, when I don't have the triangle out front, but I put them in parentheses, this means the area. And that's equal to C prime EF. I need to justify this. This is not obvious from the picture. Why would those triangles have the same area? We're going to think, so every triangle has three bases, not just one, and therefore three corresponding heights, the perpendicular distance from its vertex to the baseline. So both of these triangles, B prime EF and C prime EF, can be regarded as having the base EF. Now, that's a nearly vertical line, but it can still be the base, right? Now, the height of the triangle B prime EF, which is shaded in green here, the height of the triangle B prime EF relative to this base EF is the perpendicular distance from B prime to the line EF, right? It looks like this is actually close to being an altitude of it here, but it's the perpendicular distance from B prime to EF. The height of the triangle C prime EF, shaded in blue here, is the perpendicular distance from C prime to the extended line EF. It's this height. But this line here, B prime, C prime, and this line here, EF, are parallel. And therefore, the distance between B prime and this line matches the distance between C prime and this line. And so those two triangles, namely B prime EF and C prime EF, those two triangles have not only the same base, but equal heights. And that means that if the area formula for the triangle is 1/2 base height, then I guess they have the same area. So that's because these triangles have equal bases. Well, they have not equal in the sense of equal measure, but the same base. So the same base, and they also have equal heights. It's all because those lines are known to be parallel. B prime, C prime, and EF are known to be parallel, and therefore the perpendicular distance from B prime to one line agrees with the perpendicular distance from C prime to the same line. Okay, so those triangles are equal in area. So what? Well, if those triangles are equal in area, then we get an equality of their negative portions, right? So these triangles are, each of them is part of this larger figure, which is the DEF triangle. And so we can take the complements of these triangles within the larger figure, and then we know that those things have equal area too. In other words, we'll take the equal triangles in green and blue, and we'll just subtract each from the larger picture, the triangle DEF. And we'll get negative versions of those, which must have the same area too, because we're subtracting equals from equals. So therefore, what do we conclude? Triangle, what happens when we take away the green triangle from the original picture? We get A prime, B prime, F. So A prime, B prime, F. And the area of that agrees with the area of what happens when we take away the blue triangle from the original picture. We get A prime, C prime, E. A prime, C prime, E. So subtracting the green and blue triangles known equal gives us two triangles that are then known equal in area anyway. They're certainly not congruent. We don't expect them to be congruent, but they're equal in area. So they're both kind of long and thin in this picture. It's this one and that one. Okay, so what? Well, let's see what we can do with that. Now, if these triangles are equal, then what we're going to do is we're going to start thinking about ratios of areas. Okay, I've reshaded to call attention to triangle A prime, C prime, E, which is the one here. So I've shaded it in pink and underlined it in pink here. And I want to focus on this triangle. This is what happens when we removed the blue triangle, whose shading I've also taken away from the picture. So what we're going to do is we're going to look at this triangle in relation to its smaller triangle, A prime, B prime, C prime. So what I want to do is I want to look at the relationship between the area of A prime, C prime, E, and the area of A prime, B prime, C prime. The way that I've written it is somewhat confusing. It'll make more sense if I write A prime, E, C prime. So A prime, E, C prime, and A prime, B prime, C prime. Now, I want to consider, so obviously it's greater than 1, right? At least in the picture, A prime, E, C prime is bigger than A prime, B prime, C prime. So the ratio between these areas is going to be greater than 1. But we can say an awful lot more than that about this ratio. These two triangles, this one shaded in pink, and the A prime, B prime, C prime, which is here, doesn't have its own shading, but it's right here. Well, every triangle has 3 bases, right? And every triangle has 3 heights. But from the right perspective, these triangles have the same height. So I want to consider the base of this triangle to be A prime B prime here. And its height then will be the perpendicular distance between C prime and the line A prime B prime. Similarly, I want to consider the base of the triangle A prime E C prime to be this line AE, in which case its height is again the perpendicular distance from C prime to the line A prime E. So from that point of view, these triangles have different bases, but they have exactly the same height. The height is the distance from the point C prime to that line. Now, if they have different bases and the same height, then obviously they're going to have different areas, okay? But the ratio between their areas, if the base is constant, will be the ratio between two formulas like this. And the heights in those formulas will cancel because they're equal, right? So that means the ratio, and the 1/2 obviously will cancel because that's a constant. So the ratio between the areas of these triangles is the ratio between two formulas like this. But in those formulas, the heights are equal and the 1/2 are equal. And so the ratio between the areas is equal to the ratio of the bases. So this is equal to the length ratio, length AE divided by length, it's A prime E, length A prime B prime. So this length here divided by that. In other words, the ratio of the areas of those two triangles is equal to the ratio of the bases of the triangles because their heights are equal. That exact argument, I'm not going to reshade, that exact argument can be carried out for this other long skinny triangle here, A prime, B prime, F here. So similarly, so what do we get here? A prime, how do I want to phrase this? A prime F B prime, area of that, divided by A prime C prime B prime, area of that. So talking about this triangle here in relation to the smaller, they have the same height. The height is the perpendicular, so if the base is here, the height of these triangles is, in both cases, the perpendicular distance from B prime to this line A prime F. And so for both triangles, we can take the base of the smaller triangle to be A prime C prime, and the height will be this distance. And the base of the larger triangle will be A prime F, and the height will be, again, this distance. So they have the same height. And so just as before, the ratio of their areas is the ratio of their bases, but their bases in this case will be A prime F and A prime C prime. So the area of their the ratio of the areas is equal to the ratio of the bases. Okay, so we got a lot going on here. We got some equal areas and we got some ratios of some areas, and everything's coming together, although it might not look like it. So notice that this triangle, A prime, E, C prime, that's this, okay? So this is the same thing as this. And furthermore, I'm running out of interesting colors here. This triangle here is the same thing as this triangle here. And likewise, this is ABC. That's ABC. That's the same thing here. So the left-hand side of this equation is actually the same thing as the left-hand side of this equation because it has literally the same denominator, and the numerator is exactly these things which we worked so hard to show equal here. And so the left-hand side of this equation is in agreement with the left-hand side of that equation. And so what do we conclude? We conclude that their right-hand sides are equal. So thus, what do we conclude? A prime E over A prime B prime equals A prime F over A prime C prime. Now, let's use our notation carefully here. A prime E could also be called DE because A prime is D. And A prime F could also be called DF. And if so, now remember that the triangle A prime, B prime, C prime was simply a copy of the triangle ABC in the sense that it was congruent, right? We proved them congruent. And so any length A prime, B prime can be replaced with a similar length AB. So we get from this DE over AB is equal to DF over AC. And that is the statement of proportionality between the two original triangles, ABC and DEF. And this shows that, yes, indeed, if triangles have equal angles, then they have proportional sides. And that completes this proof.